Welcome everyone, and thank you for joining our tutorial today. We are excited to have you with us and look forward to sharing some valuable insights. My name is Qinglin, and this is my partner Zhaocheng. We both come from Huawei Nova Arc Lab and have been deeply involved in online advertising for several years. This tutorial also benefits from the valuable suggestions of our colleagues Chuhan, Jieming, and Professor Chen from Renmin University of China. The title of our tutorial is Feature Interpretation, Tracing Behaviors of Features in Recommendation Models. Let's get started. Let me walk you through the outline of our session. We will begin with the introduction, where we will provide a brief overview of the topic and set the stage for our discussion. Next, we will dive into techniques evolution, exploring how methods have advanced over time in the field of recommendation models. Then, we will look at diverse applications in industry, showcasing how these techniques are being applied in various industries, including online advertising. After that, we will discuss some remaining problems, the challenges that still exist in the field, and the potential areas for further research. Finally, we will wrap things up with a summary highlighting the key points we have covered during the tutorial. In introduction, first, we will provide an introduction to feature interpretation, explaining what it is and why it's an important aspect of recommender systems. Next, we will explore how feature interpretation benefits recommendation systems, discussing the ways it improves model transparency, efficiency, and decision making. We will then cover the core techniques of feature interpretation, where we will look at the fundamental methods used to trace and understand feature behavior in recommendation models. Finally, we will figure out the challenges of feature interpretation, focusing on the limitations, complexities, and open questions that still need to be solved in this area. In today's digital age, we are experiencing information overload with over 600 million products on platforms like Amazon and more than 75 million news articles published daily. It's impossible to process all the available information manually. This makes information selection not only necessary but critical to ensure users receive the most relevant content. Feature interpretation plays a key role in helping recommender systems tackling this challenge effectively. Recommender systems help us select and filter information based on our individual needs. They play a vital role across various domains such as e-commerce, news, videos, and even food recommendations. Whether we are working, entertaining, or studying, these systems are consistently assisting us in navigating the vast amount of information available. As a result, we are able to live more efficiently with the support of recommender systems, making smarter, faster choices in our daily lives. There are three basic elements of a typical data-driven recommender system. Data, the quality of the data, including samples and features, determines the upper bound of the mode performance. This data is essential for modeling user preferences and training our models. Second, the model. This refers to the type of the model to be learned, whether it's a deep model such as DNN, deep cross-net, deep FM, or shallow models such as logistic regression, XGBoost. The choice of model affects how well the system can capture complex patterns in user behavior. Objective. This is the objective we want the model to achieve, whether it's maximizing accuracies, enhancing user engagement, or optimizing for specific outcomes. Features are the essential materials for decision making in recommender systems. They provide descriptive information about the user, the item, and the context in which the recommendations are made. Unlike image and text data, which can often be processed directly by machine learning algorithms, recommendation systems rely on human engineered features to supply the necessary decision materials. These engineered features help the system to understand complex relationships and preferences, ultimately leading to more accurate and relevant recommendations. Human engineered features always can be categorized into 3 types: categorical features, numerical features, and multi-hot features. Categorical features, these features represent distinct categorical such as age, groups, and gender, or item attributes like brand names or product categories fall into this category. Categorical features typically require encoding methods such as one-hot encoding to be effectively utilized in machine learning models. They help the model understand different classifications and preferences. Numerical features, some features consist of quantitative values and take any numerical value within a specific specialized range. Examples include user ratings for products, prices of items, or the number of purchases made. Numerical features provide precise information that allows a model to identify trends and relationships effectively. Multi-hot features are a special type of categorical feature. Whether multiple categories can be activated simultaneously. For instance, in a movie recommendation system, a single movie may belong to several genres like action, comedy, and drama. The feature vector for that movie would have a value of 1 for each genre it represents, resulting in a multi-hot representation. This approach captures the complexity of user preferences and item characteristics more comprehensively. Feature interpretation is crucial for understanding how features contribute to the performance of recommendation models. The recommendation model operates as a function of feature sets, meaning the quality and selection of these features directly impact its effectiveness. By identifying high quality and informative features, we can significantly enhance model performance and provide more accurate recommendations. Conversely, recognizing redundant and noisy features is essential for reducing the online serving burden. Removing these unnecessary features can streamline the model, leading to faster response times and more efficient processing. Additionally, understanding important features is vital for efficient model design. By knowing how different features interact with each other, we can create more sophisticated model and complex user preferences. At the core of these techniques lies the goal of interpreting which features are truly important. This interpretation not only improves model accuracy, but also provides valuable insights into user behavior and preferences. In industry, Interpreting important features is not just a technical task. It's essential and can directly impact revenue. By understanding which features matter the most, business can optimize their models for better performance, leading to improved customer satisfaction and ultimately increased income. However, challenges arise from the logging systems, which often contain a lot of noisy data. This makes it difficult to distinguish between useful and irrelevant information. On top of that, the feature candidate pool consists of thousands of potential features, making feature selection and interpretation even more complex. Controlling feature quality offers many benefits. It can improve model accuracy by focusing on the most informative features, reduce computational costs by eliminating redundant or noisy features, enhancing online serving speed, ensuring more efficient and faster responses, lead to better user experience, and in turn drive business growth. Feature importance is a systematic metric that covers many aspects of both single and cross-feature performance. At the level of a single feature, key factors include cleanness, whether the feature is free of noise and errors, informative value, how much relevant information the feature provides for the model to make accurate predictions. When considering cross-feature interactions, important factors are low redundancy, ensuring that features do not overlap excessively in the information they provide, which helps in avoiding redundancy, high interaction, the degree to which features work together to reveal meaningful patterns and relations, which can significantly improve model performance. By systematically evaluating these aspects, we can select the most valuable features and design more efficient and effective models. Existing feature importance involves combining both statistical machine learning models and expertise knowledge to achieve accurate assessments. Statistical or machine learning models, these models help by tracing which features contribute the most to the model's optimization through techniques like feature importance scores, permutation importance, or sharp values. We can quantify how much a feature impacts the model's predictions. This data-driven approach allows us objectively rank features based on their contribution. Expertise knowledge. Well, statistical methods are powerful. They need to be complemented by domain expertise. Experts can identify important features based on world knowledge, understanding the real-world meaning of features, user behavior patterns, or industry-specific factors that may not be captured by model alone. This blend of expert insight with data-driven analysis ensure a more comprehensive understanding of feature importance. Together, these two approaches allow for more accurate and reliable feature importance estimation, leading to better model performance and decision making. Estimation feature importance in industrial scenarios comes with curse of dimensionality. In many real-world applications, the feature candidate pool can contain thousands of features, but only a limited subset, often just hundreds, can be served online due to the computational constraints. This makes it difficult to accurately identify and select the most important features for the model. From accuracy concern, in high-dimensional spaces, statistical models often lose accuracy. The complexity of managing a large number of features can reduce the precision of feature importance estimation, leading to suboptimal results. From the efficiency concern, handling large feature sets combined with billions of samples poses a significant storage and computational burden. Processing and optimizing these large data sets requires immense computational resources, making it challenging to maintain efficiency in both training and serving phase. Addressing this challenge requires balancing feature selection, model accuracy, and system efficiency to ensure that the best features are used without overwhelming the system. Cross-feature interaction, also known as Cartesian product of features, is key to unlocking deeper insights in recommendation models. A feature's informative value is not only dependent on itself, but is also heavily influenced by how it interacts with other features. For instance, longitude and latitude each provide useful data points on their own, but when combined, such as through their Cartesian product, they yield precise geolocation, which is far more informative than for recommendations. However, as the number of features increase, the interaction effect grows exponentially. This is because the Cartesian product of features involves combining all possible pairs or sets of features, which makes the model more complex and harder to compute. Without properly managing these interactions, we may miss out on critical relations between features that can significantly enhance model accuracy. Model selection bias is a critical issue when estimating feature importance. The accuracy of importance estimation is often limited by capacity of the model being used. In other words, if the model itself is not capable of fully capturing the complex relations between features, the feature importance scores derived from it also be biased or incomplete. This bias is particularly hard to eliminate because it stems from the inherent limitations of the model architecture or algorithm. No matter how sophisticated the statistical methods are, they can only reflect the feature importance to the extent that the model can learn and represent the underlying patterns in the data. Therefore, while it's challenging to completely mitigate model selection bias, combining these estimates with domain expertise and additional techniques help achieve a more comprehensive understanding of feature importance. The interpretation issue of black box models, particularly neural networks, presents a significant challenge in feature importance estimation. When we estimate feature importance, we aim to understand which feature the machine learning model relies on to make predictions. However, neural networks and other complex models often operate as black boxes, meaning their internal workings are not easily interpretable. This lack of transparency makes it difficult to ascertain how specific features influence the model's decision. Let's start begin. In industrial applications, we often encounter a situation where there are thousands of features available, yet only hundreds can be utilized in an online environment. This limitation poses significant challenges for feature interpretation and model performance. The complex interactions between features make it hard to understand how they influence the model's predictions. Additionally, the models themselves can introduce biases, complicating the interpretation further. Thus, a feature interpretation system acts like a funnel. It filters through many features to identify the most relevant ones for effective online use. This process helps optimize model performance and ensures that the insights gained are clear and actionable. Let's give the time to my partner, Zhaocheng. How to design filters.
Okay, thank you everyone for waiting this long. And now I will talk about the details of our techniques. So techniques have evolved for a very long time, from statistical-based method to white box method and black box method, and currently maybe our knowledge-driven method maybe become popular. So let's recall what is feature importance. So feature importance has single feature cleanness, low cross feature redundancy, and informative for targets. So let's solve the first question: how to know the single feature cleanness. So typically, important feature carries more information for our task, and those sparse and so from a statistical point of view, those sparse and low variant feature is hard to learn. So we can design some filters like variance filter or zero filter to find these features and remove them from our system. For example, the feature in the blue box called currency, they have the same value. If we put it in our recommender system, there's no additional information for our prediction task. And for the zero filter, we also provide example in the green box. So in this feature, there are mostly zero. Only a few of them are one. So we think there are a lot of empty value here, but there is still a little challenge in here, is that whether these features with high with many empty values are really useless. So the reason is not. For example, if our task is predicting whether this user is likes the car game, the car game feature is very important. So we want to use them with this value in our model, but this is hard to learn for a simple neural network, because it contains many non-information. So we can design some specific model structure for this. For example, we can reference to the wide and deep structure and put some very sensitive features to the white tower, so they can directly link to the prediction prediction output and provide its information. So the second aspect is they have low cross-feature redundancy. So important feature should have low redundancy with other features, because redundant feature will increase the computation burden, and they created many noises for more advanced models we will describe later, because they share many information, and their importance are dependent with each other. So if a model assign importance to one feature, it may share the information with another feature. And finally, if you remove these two features altogether, there is no information is provided. So if two features are highly dependent, then they are redundant. There are many. In this table, I have given an example. For example, in this the app ID and app name, even though they are not exactly the same, but their value is almost the same. So they provide the collinear information. If you train them into the model, these two features may share information equally, but if you remove them two altogether, then no information is provided. So there are many tools. There are many statistical tools for solving this problem. For example, for the sparse feature, which is the categorical feature, we can use the mutual information and adjust the mutual information to measure whether these two categorical features are correlated. And for the dense feature, we have the Spearman rank and the Pearson correlation to know whether they are collinear. And between sparse and dense feature, there are some techniques called F-test. For example, like ANOVA can test whether this dense feature influences the categorical feature. And for the multi-hot feature, multi-hot feature is different from the sparse and dense one because it had added a new dimension, which is time. For example, we have multi-hot features like how many apps the apps user clicked in past fewer months. So we cannot directly measure the correlation between this one and the other two type of features. But within the multi-hot features, we can use the cross correlation tools to measure the dependencies. Now we come to our third important feature importance, which is it is informative for our target. And basically, if you treat our target, for example, in a CTR task, the click as a categorical feature, we can measure the feature dependencies using the method I talked about. For example, if we have many sparse features, we can measure the mutual information and adjust the mutual information with the click behavior, and we can know which one can provide more information for click. And for dense feature, we can use the F-test. And after we have the importance score, it is better for us to normalize them into between 0 and 1. And after the normalization, we can rank them and select the top key feature for our following system. So about what I have described, this many single aspect feature importance. But if we want to combining them, how should we do? So there are many techniques have been doing this. The basic idea behind this is they are formulating a multi-objective optimization to make the model consider redundancy and relevancy altogether. For example, they have one objective of maximizing relevance, which is compute the dependency between the feature and label, and they have another objective is minimizing the redundancy, which is feature-to-feature dependency. And they can combine these two objectives with a division or with a minus to align the range of these two objectives and get a final objective. For example, you have there is a work called maximize relevance and minimizing redundancy, which is MRMR. They designed this algorithm and tested on a large gene dataset, and selected the features have achieved the best performance comparing to other statistical methods. And this method has been also listed on the Google Cloud feature selection tools. And to sum up for the statistical-based method, the pros of this method is extremely efficient and easy to implement, suitable for large-scale dataset. And it is good at handling feature redundancy and single feature filtering tasks. But the cons is it has a limited capability in modeling feature to label nonlinear relationship. It also has a limited capability in considering all feature interaction effect. And it has a difficulty in handling heterogeneous feature type. For example, the multi-hot feature and the sparse feature and dense feature. Finally, the elimination estimation result is always inaccurate. but it is useful in our industrial application because we can handle the basic single feature cleaning and the feature redundancy task. This is very important for many downstream other filters like neural network model-based method, because they cannot discriminate between whether these two features are redundant. So where are we now? We want to find very important feature accurately. So we first filter some very low quality and redundancy features with some vanilla statistical-based method. So next step, we want to know how to incorporate recommendation models, nonlinearity, and feature injection into consideration to make it more precise. So like here, I have placed the 3 filters, and the first one is the statistical model, and it can remove redundancy and remove low quality single features. And now we described the second and third filter. For the next 2 filters, they are more focused on the informative for targets, because no matter the white box model or the black box model, they provide a very complex nonlinear relationship with than the statistical method. So let's introducing a concept called a surrogate model-based method. So the idea behind this is very simple. So we first use a machine learning model as a surrogate to build the nonlinear relationship between our feature and our target. That's the first step. We train it onto converge. And then we use some interpretation method to know how each feature contributes to the final prediction objective. And the interpretation method is different from model to model, but a simple heuristic here is interpreting how each feature contributes to the optimization process. And after we have selected, after we have know which feature contributes most to our task, we can find the most important features as a small feature set and use it to retrain our machine learning models. And the retrain results can be used for online serving. So the evolution of the surrogate model for the recommendation task have evolved for a very long time, from the simplest logistic regression to the neural network, and possibly in the future we have the large language model. And the easiest, the simplest white box model is the linear model. So the linear model, some examples of linear model include logistic regression and linear regression. And if we add some feature interaction into consideration, we have the factorization machine. So basically, their idea is doing a weighted sum of different features, and the features, the feature weight can be indicator of how much this feature will influence the final prediction result. If this the absolute value of a feature is very big, then it possibly will influence more to the prediction result, and vice versa. So we can, so it is very easy to interpret. We can just select the features with big value. But during training, adding a sparsity regularization to force model rely on only important features is very useful in our industrial experiment. There are 2 very classical types of regularization, including the ridge regression and the lasso regression. This will force the neural network focus on only small subset of feature, and if the model rely on these features, then possibly they can contribute many information to the target. And the second type of white box model is the tree model. And the tree model don't have some a coefficient that we can observe directly, but the no split criterion also can be used as a feature interpretation criterion. If we look at the left side of the picture, we have a feature, and if we can calculate after a split on this feature, feature, how the prediction result information performance increase. For example, calculating the gene index or the purity. But if we extend to this very vanilla tree to random forest or XGBoost, we can calculate the statistics of the stabilization criteria to know which feature provide most information. There are some examples, including the total gain, which is the total gain across oscillate the feature is used in, and total cover, which calculates the total coverage across all oscillates the feature is used in. And this method has been demonstrated in the XGBoost documentation. And we also constructed a feature selection benchmark called ERASE to compare different feature importance estimation methods. And this picture has showing the comparison between different white box method. Generally, shadow model, white box model based method outperforms than no selection, and the tree-based method are slightly worse than the regularized linear model. To sum up for the white box model-based method, the pros is they can modeling the basic nonlinear relationship and feature interaction, improving filtering accuracy. And they can easily be rapid in some mature big data platforms like Spark, and scales to 1,000 features levels with very large data set. And they can support many feature types relying on feature embedding. Because this method rely on feature embedding, and if you put the sparse feature, dense feature, and multi-hot feature into the feature embedding, then to this model, there is no difference. And the course of this method is they fails to model arbitrary nonlinear mapping and have gap between the mainstream neural network-based method, because in industry, almost all platform use a deep neural network right now. And they suffer from the feature redundancy issue. But it has been partially solved by the statistical-based method I mentioned above. And for our industrial application, it can be used as some pre-filtering phase because we in industry have having very mature big data platform that can support 1,000 level feature sets and these simple machine learning models. And they can consider basic nonlinear relationship and feature interaction. So now we have our second filter is white box based model, and in our industrial platform, we use this model to reduce feature number from 1,000 level to 100 level, and we deploy these white box models on platforms like Spark. So let's enter the final filter is a neural network, which is a black box model based filters. Using neural network to surrogate choose feature interaction and feature to target nonlinearity is very good because MLP is a universal approximator. So ideally, it can provide the most accurate approximation given enough data. But the challenge here is how to trace in feature contribution given its black box nature. So here, many methods use a very simple assumption that the first layer's weight plays a key role. So the first layer's feature weight didn't interact with other features, so it is more controllable. If we set the first layer's feature weight to 0, then it won't enter the following model structure and won't interact with other features also. But this assumption ignoring the following layer's nonlinear transformation. So the most ideal solution is assigning a 0 weight, which I can also call gate for a feature, for unimportant feature. Because if we set some non-zero values, it may be magnitude by the following nonlinear transforms. So one of the earliest work is called LaSonnet. What it do is it's regularizing the norms of the first weight matrix. They forcing the norms of the first layer weight matrix less than a chainable skip parameter, and meanwhile they trying to regularize this skip parameter. So the first layers weight matrix will become the normal will become really small. But controlling a weight matrix, the norm, is a constraint optimization problem. So if we want to use this method, we cannot use the classical backpropagation directly. So in this work, they use a proximal gradient descent to solve this problem. So what we do is once they calculated the gradient of the first layer's weight, and they try to find the proximal update that can make it less than the skip parameter theta. But can we do better? Yes. Instead of controlling a weight matrix, we can control a weight scalar. So another work and the following three work using the same thought. So they assign a gating weight for each feature, and they train it to know which feature should be more important. And for the STG method, they assume that the features are sampled randomly to enter the following neural network, and the sampling sampling distribution follows Gaussian distribution. And they want to learn the mean value of this Gaussian distribution. Because high mean values feature indicate that this feature is more likely to be selected to fit into the following neural network. Otherwise, it is less likely to be selected out. And those features are selected in a higher probability are more important. But the difficulty here is that they cannot train the sampling behavior. Because it is non-differentiable. So they use the reparameterization trick to make the sampling behavior differentiable. And they also use a hard sigmoid to constrain the gating weight between 0 and 1. Otherwise, this gating weight may become really large or really small. But here is the problem. If we treating the sampling probability as 0 or 1, we can use the Bernoulli distribution to make it more reasonable. So the following two work including AutoFuse and FSAD, they modeling the gating weight as the Bernoulli distribution, and they want to sample the features based on the Bernoulli distribution, parameterized by the probability the function is important. So the high if the feature they calculate the feature gate equals 1's probability to indicate whether this feature is more likely to be selected out. If yes, then this feature is more important. And they also train this sampling probability with Gumbel softmax to polarize the gate weight and make this sampling differentiable. And the following experiment shows that this distribution is better than the Gaussian distribution described in above slide. And the next question is, can we polarize the gating weight harder? Because we really want to make the sampling behavior like a 0-1 select problem. So the answer is yes. The next technique called RPFS, it is trying to use a more polarized gating function to make the feature importance estimation problem into a 0-1 selection problem. So the gate they are using is listed on the right side of the slide. And basically, they add a very small epsilon at the denominator of this function. And if this and if x is very big, then it is then this function is approaching to 1. And if this 0, if x approaches to 0, then this gate value is also approaching 0. But this gate is non-differentiable, so they designing a piecewise function to ensure the differentiability when x equals 0. And the experiment shows that this trick is very effective, but also increase the difficulty for training this neural network. And in our benchmark series, we also compare the performance of this gating-based black box method, and this experiment result shows that they outperform the white box based method, and the polarizing trick shows higher capability. But in our industrial application, we found it's hard to train. So the limitation of this method is that they only consider the first layer's weight magnitude as a feature importance. So next question is, are there other techniques that can consider all layers nonlinearity altogether? And let's enter to another paradigm of black box based method, which is called removal based method. So the idea here is very simple. It's just to remove a feature from the input layer and record the model performance drop. And you can see from this curve that when you have a feature, the loss is comparatively low. But when you remove it, the loss will increase by some extent. And the loss difference here can be viewed as the feature importance. And this method have taken end-to-end nonlinear transformation into consideration, and it also considers all feature interaction, because what you are comparing is you have the feature and you didn't have the feature. And it is robust to use because no numerical hyperparameters are needed in this setting. And we can do the removal-based method in both training stage and the validation stage. So for the training stage, there's the technique called leave one query out. Also, for short, it's local. It remove a feature, retrain, and see the model, the training performance drop. It has a linear training complexity, but the performance really well. But in industry, the training complexity is too huge and cannot meet our efficiency criteria. So we want to be more efficient. So if we want to be more efficient, we can switch to the removal-based feature importance in the validation stage. The basic idea between the validation stage removal is that we cannot remove them directly because in the training stage, the computation graph has already been fixed. So we're using some baseline features. So the baseline features here means that these features do not have any information. And we observe the validation loss change when we switch in the original informative feature to the non-informative baseline features. And in the right down of this slide, provide a classical permutation algorithm belongs to this paradigm. So what they do is they find, they iterate the feature set, and for each feature, they permutate their values, and to compute the difference between the validation loss before permutation and the validation loss after the permutation. And this operation have a linear validation complexity, but it is still applicable in scenarios with moderate feature and data sets. But in industrial, if we have 1,000 level features, it still takes too much time. So the next track question is how to define. Sorry. The next question here is there is a hyperparameter. Is how can we design a non-informative feature? So there are many ways to design to say a feature is non-informative. Like the example I said before, there is a permutation operation, and also we can set all feature value as 0 which we call zero embedding, and we can also set the features to be the mean value of all samples. So which one is better? And we conducted an experimental study shows that baseline feature closest most to the decision boundary performs better. And for example, in the right graph, and the mean baseline is the most recent baseline feature from the decision boundary, because in recommendation system, the negative sample always dominates the positive samples. So if we use the mean embedding, it always contains the negative information. So those zero baselines and smoothing baseline, which is using a smoothing operator to make it lose information gradually, performs the best. But in industrial, this is still slow because it will take linear validation time. So the next step is seeking for some approximation. And multi-SFS and Shark applied this technique. They are trying to use the first-order Taylor expansion, first-order Taylor approximation for validation stage removal. If we view the loss as a function of features, approximating the problem becomes how will the loss change when we're switching our X value from the informative ones to the non-informative ones, which all can be represented from the numerical value perspective. And we can just use the gradient plus multiply by the difference between features and the baseline features to get the feature importance. With this technique, we can finish the evaluation in one validation time. But we always want to ask, can it be faster? And multi-FS researched this question. They estimating removal-based feature importance at early training stage. Because important feature becomes sensitive at early stage of training, and detecting feature importance at early stage with small batches will lose very little precision according to our industrial experiment. The real world example is that with 10% samples, the performance will drop about 10,000 percentile. So basically, it is very useful. And we also compared the removal-based feature importance and gating-based importance in our ERASE benchmark. And the result shows that gating-based method shows higher performance upper bound, but very sensitive to the hyperparameter tuning. And the removal-based method has no hyperparameter and is very robust to use in different industrial scenarios. So even though the accuracy may lose a little bit, we still apply them in our platform. Now we have fulfilled our third filter. It's using black box model. So for this model, it uses the online neural network architecture to select the 100 features, select from 100 features to another 100 features for serving online. But this system is vulnerable when samples are very sparse or very dirty. So let's recall our model selection bias. If our model is good and we provide it with very dirty data, the estimation result, feature importance estimation result is also not very clean. So how can we handle this? That's when we should use the language, the knowledge-based method. The recent work called LLM Select uses a large language model to use their domain knowledge to give a score for each feature for a task. And they found that they achieves almost the same precision with the previous mentioned data-driven method. But it is hard to be applied in our industrial system because our feature contains very fine granular domain information. And a large language model may not learn that well before. So more researches can be done in this area. And we have talked all about all our techniques, and we can know other applications in industry. The first application is conducting higher order composite feature interpretation. They also can be used the gating-based method and removal-based method. For the gating-based method, two techniques are introduced here. The first is auto-fizz. This model assigns gate value for each feature interaction and train it like using the DARS method. And those gates with bigger information will be selected out, and this feature interaction is treated as important. And another technique is OPTFS, and this is a little bit different because it assigns weight gate to each single feature. And if we know these two single features are both important, then they think this value is also important. Otherwise, they think this interaction is not important. Another method is called another method uses the removal-based paradigm. It is called RecSys. It detects the important interaction with the Newton matrix approximated second-order gradient. So the basic idea here is if we use the first-order gradient to approximate which feature contribute most to our objective, then we can know how other feature provide information for this importance. And but because second-order gradient is very complex, contains n square storage and training time, so they use the Newton matrix and to shrink it to linear complexity, which is very fast. We also deployed this technique in our feature selection system. But when we come to the higher order, things become very difficult because the feature interaction increase exponentially. So some intuitive methods are used to address this issue. Here we describe a technique called autocross. So for autocross, each turn they will greatly select the best feature interaction and expand to the next order. You can see this. So this graph. They first expand to AB, AC, and CD. Then they find that AB performs the best. Then they extend the AB to the ABCD, and more. But this performance is very greedy and cannot achieve the global optimal. And more researches can be done in this area. And in industrial, also there are many domains are modeling altogether because the multi-domain recommendation can reduce the cost of model development and maintaining. But how to find some domain-sensitive features? So here the idea is the feature value importance distribution are significantly different in different domains. So we can first perform a feature importance estimation at a feature value level. Then we can calculate the distribution divergence between the feature value importance between different scenarios. And the big one are treated as the domain-sensitive features. And the third application is the efficiency interpretation in large-scale system, which I have described above. We can use a funnel-like system to filter features step by step and get the final online serving. The final application is we can do the fine granular feature interpretation. For example, like embedding size search, because this problem can be viewed as a special feature interpretation task where features can be viewed as a dimension. There are also two types of techniques. For the gating-based method, we have auto-dim. It is a gating method select the embedding size with DAS paradigm. And another one is SEEDS, seeds. And it uses gradient information like I described above to select the embedding size with embedding sensitivity. There are also some remaining problems in this research area. So the first one is online-offline misalignment, because all methods that I mentioned above using surrogate model are trying to optimize the offline metric. for example, the AUC, and they cannot guarantee the online performance is aligned with the offline. So some current solution is relaxing the ablation criteria based on some feature selection curve. But it's still hard to determine how what relaxation degree we should use. And for future, we can designing feature selection algorithm based on online feedback. And second is very complex feature interaction. Because of feature interaction, the feature selection problem is NP hard. And feature quality are determined by their interaction, and feature selection is a combination optimization problem. So our current solution is using funnel-like system to decrease feature interaction complexity and making approximate algorithms easier to achieve to global optimal. So the future direction is designing interaction-aware algorithms, for example, using higher order gradient. And third problem is the surrogating bias, because surrogate model quality affect selected features quality. So model cannot be guaranteed to perform well in all scenarios, and practitioners cannot distinguish feature defect or model effect. The current solution is using prior knowledge to compensate the local optimal result, and the future direction is automating the current solution with a large language model. And in summary, feature selection is an important problem in recommendation system because keeping informative features can improve millions of profit. However, feature selection is an NP hard problem because features are interacted with each other. We cannot examine every combination. And the third is feature selection is a system problem other than a single algorithm, because it has a trade-off between accuracy and the efficiency. And the statistical model is very efficient, but cannot consider complex interaction. And it is suitable for reducing redundant features. And the shallow and wet box models is less efficient, but is mature in large-scale machine learning systems. It is suitable for reducing huge feature sets to MLP process level. And the MLP provides highest accuracy, but cannot scale well. It is suitable for the quality control in the final level. And more application can be extended from this technique. For example, embedding site search, feature value importance, etc. And we should always be cautious by the feature selection result because it may be because of your model's failure, and it has a misalignment between the online performance. Okay, thank you very much. And any questions are welcomed.
Any questions?
Okay, thank you for your talk. Can you hear me? Yeah. So early on, you mentioned that you instead of using white box methods, you could, for example, use the first layer of a neural network, a multi-layer perceptron. Have you tried this, and how well does that work compared to logistic regression methods?
Sorry, I think the voice is a little bit small.
Okay, so early on you mentioned the concept of using the first layer of the weights for a multi-layer perceptron to select features. How well does that work compared to logistic regression methods, like
compared to which method?
Like linear methods, like logistic.
Oh, okay. Yeah. I have a slide for that. It basically outperforms than the shadow model-based method. Sorry, wait for a second. Let me try to find it. Yeah, here is the performance. We tested it on 4 public datasets and found that method using the first layer of MLP performs better than Lasso, GPDT, Random Forest, and XGBoost. Yeah, I think it's because neural network can model very complex nonlinear relationship compared to these shallow models. And also maybe because the current mainstream model are neural networks. So if we select it with neural network, we can get better result.
Okay, fair enough. Thank you.
So any other questions? No? Yeah. Yeah, I think we can call it an end. Okay, thank you very much.